Hey, what's up? So, in the last video on Quaternions, I had a little bit of a brain fart towards the end, but, so I'll address that quickly and then get into the content for this video. I might get confused at some point again because Quaternions are confusing. But I was looking at this line of code here, and what I was forgetting is because you're normalizing, so if you're not familiar with normalization, then please watch the first video. But what I forgot was, so basically when things are normalized, you could multiply all four of these by some number, a scalar. That's just a fancy word for a number. And it will be pretty much ineffective. Well, if you multiply it times a negative number, I'm not sure if it reverses orientation. I'd have to think about that. But like if you multiply them all by the number 200 or something, so the normalization process is just going to basically undo that. And it might do more than that, but it's going to undo it. So here, when I'm doing this 1 over square root of 2 here and 1 over square root of 2, it's the same as if you're not doing that. So I just got a little confused in the last video, but that's all. And you don't really need to be using the 1 over square root of 2 thing. But okay, so something I wanted to explain is if you have all zeros, this cannot be normalized. So I think it will crash or something, or just not. I think it will just not render the object. So this is kind of the starting point. We call it the identity. This means that you do no rotation whatsoever. And I'll talk a bit more about that. But you can also, it's perfectly fine to have like 1, 0 here. Or even a -1, 0 here. Yeah, that'll be fine. Okay, so let's start off by talking about this. Or should I show you what these do? Well, first off, 1, 0. Let me just restore this to what it's... Oh, I can do the commands here as well, as you can see. So we won't have to load up the game each time. So this is restoring the original orientation that I started with. Now, if I go 1 here and 0 here, what happened here? So red is on the other side. So we did some kind of 180-degree rotation. And you notice that the Z component is where I'm doing the rotation. Well, that language is a bit imprecise, but the Z component is where the axis is. So I'm rotating along the Z axis, which is the blue axis here. And so we can see that we actually rotated underneath because this magenta thing was at the bottom. So we rotated along the bottom here, which flipped the magenta one to the top. Or actually, it's hard to say. Both ways work, right? Do both ways work? Yeah, it doesn't matter if you rotate 180 degrees or negative 180. Same thing, right? Okay, so, but if I put a -1 here, what happens? It's the same thing. Yeah, it's a question of negative or positive. So what I'll do here to demonstrate this actually, so we're not getting a good demonstration, I'll put time here. And then after that, I'll put negative time here. Okay, I'll push play. I'll have a look-see. I'll explain in more detail how this stuff works in a bit. I just want to demonstrate, and demonstration is failing for some reason. Why is the demonstration failing? Because I have... Yeah, it's always going to be normalized to the same thing because I put a 0 here. So let's put a 1 here. Okay, so as time goes up, you notice time is getting printed. Yeah, t is getting printed here. So you can see it's like, it's on a second basis. It goes 1 second, 2, 3, 4, such. It's a number of seconds. So after 20 seconds, it will be getting close to the case of this being 0 and this being 1. If that doesn't make sense, then review the normalization stuff I talked about in the previous video. So we'll see that start to take place. Okay, so you can see it is rotating, red coming over here. And so if I wait long enough, then we'll get closer and closer to the position that I showed you before I started it, with magenta on top. But it's rotating this way, and if I do negative t, it'll rotate the other way. Let's do negative t. We'll watch it rotate the other way. So then you can imagine this would do a similar thing for each of for the x-axis, the y-axis, etc. So it's just rotating the other way, right? I think so. I wasn't actually paying attention, to be honest. It's coming up from the bottom. Let's just make sure that that's doing the same from both sides. Or, I mean, it should be rotating in the opposite direction, I think. And this one, yeah, it's rotating over from the top, if you will. It's going from this side, it's going counterclockwise. The other one was going clockwise. Okay. All right, so now I want to explain some stuff. So you need to be familiar, it's sort of a prerequisite to be familiar with the, is it called Euler's identity? I'll write two different versions. First, let's write this one, e to the, if I have it remembered correctly, e to the I theta, some angle. So this is exponentiation of the transcendental number e. This is I, the square root of -1. So if you're not familiar with e, look that up. If you're not familiar with exponentiation or the imaginary number I, look it up. But this will be equal to cosine of theta plus I sine theta. This is, I think it's called Euler's formula. Now if we plug in, let's see, I think, yeah, we plug in, was it pi, and we get, I think, Euler's identity. E to the I pi. So cosine of pi will be -1. Sine of pi is 0, right? Yep. So we get e to the I pi equals -1. This is very famous. You could also write it e to the I pi plus 1 equals 0. I guess some people like this version because, well, between all of these, it relates these numbers. You've got -1, you've got 1, you've got 0, you've got I, you've got pi, you've got e. All these sort of fundamental numbers are being related in these equations. It's just quite fantastic. And so physicists use this e to the I theta thing all the time to encode rotations. It's just a very convenient package to encode rotations. And in general, complex numbers are good for encoding rotations. So complex number will be z equals a plus bi, where a is an element of, well, a and b, I should say, are elements of the real numbers. And you could do other things. I guess you could do a and b are rational numbers, maybe natural numbers you can do. And I is the square root of -1, of course. And this in itself is an excellent sort of package or formulation for sort of packaging rotations and scalings. So each a plus bi can be viewed as a rotation and a scaling. So I feel like these should just be prerequisites for this video, but I'll review it for you. So if we have an arbitrary complex number, say this is the, let's change this to x plus bi. Or x plus yi rather. Then I'd have to change this too. Sorry, I'll get more efficient soon once I have a little more viewers here. But x plus yi. This is a waste of time, I know, to do this one. X and y, okay. It's so messy. X and y, okay. Okay, so we have x and y. And this, we're using this to represent some arbitrary imaginary number. So the whole point is that when we multiply two imaginary numbers, we multiply scaling and we multiply rotation, and we add the rotations, where this is theta. So if I have some other imaginary number, like let's say I have one here, then the angles will add, so we'll get, if this is phi, we'll get theta plus phi here. I'm not gonna write it all out, but we add the angles and we multiply the magnitudes. So another way of writing that, so any, I forget the name of it. But any complex number can be written in some form, such as, let's do it this way, I guess, r e I theta. So this e to the I theta encodes a rotation, and the r encodes a scaling. Okay, so if it's the unit circle, okay, if it's on the unit circle, then this r will be equal to 1. And then we just have an angle here. So if you think about it, any point on the coordinate plane can be represented with an angle and a magnitude, right? So this is a way of doing it. Now you could also represent this alternatively as some, why not some e to the r? Oh, but you need now like a plus or minus. And you don't see this very often, but it's just something that does this work? Yeah, why not? Something that I think about, that I find personally useful, I guess, interesting. It just r is just a number. I mean, the exponential map, right, goes like this. E to the r, e to the x, whatever. So you input any number, any real number, and your output is a positive number. It can't be 0. Oh yeah, so I guess we're missing out on 0 here as well. But close enough, we got almost all the numbers. So, but your output can only be positive. So if you have plus or minus, you could have a positive or a negative number here. And that's also going to, because we can add the exponents, so we can just get e to the x plus I y. Well, just some scalar number, some real number plus some imaginary number in the exponent. So these are different ways of thinking of complex numbers, and this is a very common way to think about it. Or this also. Okay. Anywho, let's continue. Sorry for the blinding color. I'll get rid of that right away. So we have, I need to switch these now. White, please. Black. Okay. So that was, I'll just place as a reminder. We had e to the I theta. We're going to do the quaternionic version of this next, but just as a reminder, cosine theta plus I sine theta. So when we make a quaternionic version, here's what happens. We have e to the I. Should I use I? See, now there's two different... well, I always do e to the IQ for quaternion equals. We're going to have... So this I is going to be, I think, different from the others. How does that work? I'm confusing myself again. But it's some angle, some real cosine theta part plus an I sine. See, I'm tempted to put an I here. I'm not sure what it should be called. I'm just going to call them alpha, beta, gamma. There's some I times an alpha. And I'm not sure if this should be... This is how I always write it, but I got to check if this is correct, actually. I'll put a correction in the next... Oh, wait, not equals. I'll put a correction in the next video if I'm doing something dumb here. Plus I sine beta... sorry, j, rather. Because we have I, j, and k unit vectors. And I like... These are unit vectors. I'd like putting little hats on them to indicate that they're unit vectors. Plus our k times some other angle. And note that the q here... So wait, hold on. E to the IQ. Oh, sorry. I think it should just be e to the q theta. Okay, hold on. Screw that. I think it's e q theta. Maybe. Okay. Is cosine theta. Now, for reasons that will become clear later, I'm going to instead do theta over 2. It doesn't really matter if we do theta or theta over 2. So I know it's going slow, but I think this material is quite difficult, so I think it's okay to go a little slow. We have I hat sine theta over 2. I hope this is right. If it's not right, I won't upload this. Maybe. Or just check for a comment, or check the description, or check the next video. So I don't think the I, J, and K, these thetas shouldn't all be the same, I don't think. I think there's something wrong here. I think there's something wrong. So I'll have to check it. But there's something like this. Okay? And our... but this... We have an I, J, and K. This is a quaternion, right? So we have our W component is here. So to get the amount of rotation... And by the way, what will happen is... that we are multiplying. So if we have some quaternion, I'll call it P now. When we do quaternionic multiplication for the this is theta over 2. When we do quaternionic multiplication, we actually multiply both sides. There'll be a negative here. We multiply on both sides. And that's why we do the theta over 2 instead of just theta, because we're multiplying twice. So it's basically a generalization of multiplication. So what happens is, when you go from real numbers to complex numbers, you lose a property. You gain power, you gain abilities to do things because the complex numbers are a generalization of the real numbers. But you lose something. What do you lose? You lose that the numbers are well ordered. Like if I give you some random complex number and a second random complex number, it's difficult for you to tell me like the ordering. I guess you could make up different schemes, but there's no... I think they say that you lose the well ordering or something like that. You lose this obvious way in which there's ordering between the numbers in your number system. So that's something you lose. When you move to quaternions, you lose commutativity. So that's true of rotations in 3D, that they're not commutative. If you do things in one order, but then you reverse the order, you will end up with a different state. You can try that out. So you lose commutativity when you switch to quaternions. And for me, you have to sort of generalize. You have to create a more general form of multiplication. See, because if we applied the same multiplication rule to complex numbers, then let's say our complex numbers are u and v. Okay, so u with v I, and by the way, you can switch, if you can put the negative in front. It's also basically an inverse. So for this, in this case, it's kind of the same thing. Is that technically correct? I'm not sure. I think of it as an inverse. But it works just fine as a negative. So I'm going to say I theta over 2, negative I theta over 2. If instead of just multiplying times a complex number, if you instead applied this rule, wait, hold on. These will cancel out to be... Won't these cancel out to be give you the identity? Huh. I gotta look at this more. Actually, so forget the negative. Oh, sorry. It's not negative. It's not negative. It's not negative. It's the complex conjugate. It is the inverse, actually. So I haven't talked about it, but you can have, okay, in complex numbers, you have, we say the conjugate. If z is x plus y, then this z bar is x minus y. If z is x plus iy, yeah, I hope I said that correctly. So this is the conjugate. So the thing is that when you multiply z and z bar, you get x plus iy times x minus iy, which if you do it out, it's x squared plus y squared. So if we're talking about, let's see, so yeah, that's a conjugate. I mean, sometimes you might be hearing me say, calling it the inverse. I'm not, maybe I shouldn't do that. That's maybe just wrong. I'd have to think about that. But anyways, it's the conjugate, which I've written as an inverse here. So I'll just be a little more careful and I'll write the conjugate like that. And so this one, but here the conjugate is negative, but then it's commutative, so these should cancel out. So I'm just confused. Maybe this doesn't work. My goodness. Maybe this doesn't work with complex numbers. I gotta think about this. This is good for me because I'm reanalyzing certain assumptions that I had. But anyway, this is how we want to do the quaternionic multiplication, and I think of it as a sort of generalization. And there's probably some mistakes in here. So you know, nobody's going to learn all this stuff just from one video. There's just no way. You've got to look over probably several videos. And so go out there and see if you can find if I made a mistake here. But I'm going to make more videos on Quaternions. But yeah, there's a lot of stuff to talk about, I guess. But it depends on how deep one wants to go. And if we're just talking about a game engine is one thing. But if we're going to talk about physics, then things can get a lot deeper and a lot more complicated. So I'll leave it at that for this video. Or do I want to tie this back to here maybe a little bit before I go? So yeah, so there's this real part, which is this cosine theta over 2. So if you want to, whatever the w component is, okay, we have a w component here, is 1 in this case. But the let's just say this is some other number, like it could be 1 or I don't know, what's the least confusing thing? 2? I don't know. But this will get normalized before anything is done with it. So the fact that it's getting normalized will do something to this number. So let's take the simplest example where it's just this. This is the identity, and this should represent no rotation, right? So what's the story with this 1 in the w component? Well, what this means is that cosine theta over 2 here is equal to 1. So if I inverse cosine both sides, so when you inverse cosine, you ask yourself, what is the angle where the cosine of it gives me 1? When is cosine 1? Cosine is 1 when the angle is 0. So if I inverse cosine both sides, so let me do this. I'll just write it out a little bit. Inverse cosine, which this will cancel out, and inverse cosine of 1. Then inverse cosine of 1 is 0. Because when you take cosine of 0, you get 1. And this cancels out, so it gives us our angle, or in this case, it gives us what was inside the cosine, which is theta over 2. And anytime you work with inverse cosine or inverse of these trigonometric functions, you have to keep in mind that, like, when you go around the circle, you can keep going around the circle forever. So it's like, it's theta over 2, but it's also 2 pi plus theta over 2 and 4 pi plus theta over 2. So technically it's like, it'll be like 2 pi n plus, where n is a real number, or a natural number. Be something like that technically. But so just think about it when you use inverse cosine, particularly inverse tangent, if I recall correctly, has some weird stuff because it's inverse tangent, or I think it's only defined for the region like from negative pi over 2 to pi over 2 or something. So you have to be a little careful with inverse tangent in particular. Anyway, this doesn't really change anything because our theta is equal to 0 here. Obviously, multiply both sides by 2, and that is what we expected because it's the identity, and so we expect 0 rotation. So everything you do here, remember that it's getting normalized. So it really only matters sort of the proportions between the x, y, z, and w components is really what matters. But it's not just being calculated just with ratios. It's kind of a similar idea, but it's the normalization process that we described before. So I think a good exercise is to think like, what happens when I go from this, the identity, and if I gradually change it towards where it looks like this. So maybe, for example, we could do, and similar things. You have to spend time like working these things out in your head a bunch, and playing around. I highly suggest you play around with this. You know what? I'll maybe post this in the description so you can copy paste or something, or comments. If I forget to, just please leave a comment. I'll copy paste it, or somebody else who's nice can always copy paste the stuff into the comments. So what was I gonna do? So we want to start at this. So what I'll do is, so if, for example, I could do sine of t. Let's do, first of all, let's divide t by 20. So that just things are much slower than they would be, okay? Divide t by 20, and then t here, and what if I put 1 over t here? Well, what happens when t is 0? We get a problem, don't we? So I think that's why I added a 1 here in the past. We're just starting at t equals 1, not t equals 0. But we're slowing time down by 20, basically. And then here we're saying, yeah, this is going to start close to 1. It's going to start actually at 1, and then go down, become smaller, and this one will start at, oh, this will actually start at 1. So let's do t minus 1 here now. So this will now start at 0 and climb upwards. After about 20 seconds, it will be about 1. And this one will start at 1 and get smaller and smaller. Okay, let's see what happens, what it looks like. So these are the kinds of things you need to play around with, experiment, and try to think in your head. Like, guess in your head. Actually, before we see it, guess in your head what you think we'll see. Stop, pause the video, try to make a guess. Okay, now, what's happened? It's gone very quickly to just red here. But it's not... okay, there's a problem on line 42 of the script. That's what happened, I think. I'm also going to just, here, it doesn't matter, but I'm going to revert this back to the normal position. Line 42, we had a problem. I think I removed one of the numbers. That's what it looks like. I removed one by accident. Okay. So stop, pause the video, and think what you see. Okay. So, oh, you can see now it's printing. Well, yeah, it's printing. We're getting to where it's 1 and 1. And it's coming back. Oh. Let's remember we had, before it was 1, we had, so now it's just rotating. I think it'll start slowing down with the rotation. I don't think it will pass. It'll get closer and closer to a 180 degree rotation, but it will never pass it. Pretty sure. I think that's what's going to happen. Just keep getting closer and closer to that. It does seem to be slowing down, right? You notice the behavior changed a lot. I'll run it one more time. The behavior changed a lot when we were close to t equals 1 here in the adjusted time. The behavior changed. So this behavior, can I pause it? How do I pause? But this behavior was when there was... Oh, the t was negative because I did the -1 thing. Because the +1 happens before this. So why don't we do this? We'll add +1 after we divide. Now I think things will make more sense. Because t was becoming negative, so that's why it was getting rotated in the... Or rather, the z component was getting negative. So now that didn't happen. But it did a quick rotation. Really quick rotation. I feel like it entered the game a little bit late. Let's try. Probably see the same thing. Yeah, but it started out with quite quick rotation, and then I think it just slowed down. So anyway, it's just an example of things that you need to try. Try all kinds of things and try to predict how things are going to rotate, basically. That is the idea, I think. Yeah, it's obviously slowing down. All right, so that makes sense to me. Does it make sense to you? This is kind of tricky stuff. Don't expect to understand everything in one go. It takes time and effort and practice. And if you try to do everything in one go, like one afternoon, guess what? 6 months later, a year later, 2 years later, you will have completely forgotten about it. You'll just have a vague recollection. So it's very important to me that I tend to space these things out if I'm working on something complicated like this. You know, assuming I can, assuming I have the luxury to do so, just I'll do whatever amount of time. You know, it depends a lot on what we're talking about, I guess, but anywhere from 20 minutes to 3 hours on something one day, and then the next day try again, the next day try again, maybe wait a week and try again, etc. You need to space it out because your brain makes a lot of connections while you sleep. And the next day, or it's also can be good to wait a few days, actually, sometimes, because you'll have a sort of a fresh mind. You'll have, after your brain has slept one time or several times, a lot of these neurons are connected in different ways, and you have your brain is different. It changes a little bit all the time. You'll have a fresh mind. You can make new connections. And you're only really going to properly learn something if you spread it out over time. You can't just expect to learn everything well, if you do understand things just in one day, it's still just not going to stick. So yeah, don't expect to get everything, to make sense of everything the first time. I mean, nobody understands this stuff the first time, really. If they're new to complex numbers, I mean, and the Euler equation and the stuff is tricky. All right, that's it for this time. Thanks. Peace out.